In this video, we're going to introduce the final area or area of study for the course, and that's going to be looking at differential equations and using them as a gateway to also introduce the idea of complex numbers and how to manipulate those. The main motivation is that differential equations are endemic everywhere in engineering. If you look at F equals ma, that is often a differential equation because it involves derivatives. The acceleration is the second derivative of position. If you look at things like Maxwell's equation, or Maxwell's equations, pardon me, in electromagnetics, if you look at equations for quantum theory, if you look at equations for statics, these are equations which have derivatives in them, and you're going to look at them or study them in your second year differential equation classes and possibly third and fourth year partial differential equation classes. So this is a gateway to a much larger topic that we're simply going to introduce here. So let's go back to the basics. What kinds of equations have you seen? Well, you've seen equations like x squared equals 9. And then when you solve that, you get possibly 1 or 2 or no values, but the answers are real numbers. Have an equation with algebra involved in it, you're going to get real values back. A differential equation, which is an equation with the derivative of an unknown function, here. If you're looking at that, then an example might be x prime of t equals e to the 2t. We've seen that kind of thing in our integral unit. If we were asked what function satisfies this equation, that would lead us through an integral to x of t equals 1/2 e to the 2t plus c. And again, notice these are values. The solution here is a function or possibly a set of functions as indicated up there. It's actually a family of functions depending on what value of c that we find. That's a first major change. We're going to have equations that look more like this going forward. The second issue is that our intuition is going to be fragile for this for a while, until you get some experience looking at these equations and working with them. Well, you'll see what we mean in a second. Consider this differential equation here, where x is unknown. We don't know what the function is, but we do know that its second derivative is equal to minus 36 times x itself. Take a moment to think about which of the options here fits that description, and then we'll check in. All right, well, frequently people focus on this one here, but maybe it's the exponential, I'm not sure. Oh, well, let's find out. How do we know for sure that we have a solution to a differential equation? Well, I'm just going to skim back a page first. How would we know that x equals 3, let's just take the positive version here. How do we know that x equals 3 is a solution to this? Well, we can sub it in to the original equation and check to see whether the left-hand side equals the right-hand side in the original equation with x3 as our value. Now we can see that pretty clearly here. The left-hand side is 3 squared if we propose that, that's 9. The right-hand side just is 9 to start with this part here. So definitely x equals positive 3 satisfies that equation. We're going to do the same thing here with a couple of different options. Let's try the minus 6t cubed. If, conditional here, if x is equal to negative 6t cubed, then to sub in to the equation, we need the second derivative. We can't even sub in x here, we need to sub in its second derivative. Well, how do we get to that? We're going to take one derivative, that will be negative 18t squared. And, oh, interesting, x double prime is negative 36t. So that's promising. So the left-hand side of our differential equation, let's call this 1 here, of 1 is equal to x double prime, which is equal to negative 36t's. But the right-hand side, not sure why I copied that, let's go right-hand side here, of 1 is equal to negative 36x of t. Oh, there's a discrepancy here. The 36's and the negatives work out nicely, but x and t are definitely not the same things. T is time, x would usually be position, units are different, meaning's different, everything's different, so these are not equal to each other. And that tells us that x of t equals negative 36 x of t, sorry, x double prime of t, equals that is not satisfied by our guess, our x of t equals negative 6t cubed. And so that's what I mean at first, that our initial instincts are going to be thrown off a bit, because most of the forms of the equations we're going to look at are not going to be with t's on the right-hand side. We're going to have derivatives of some function, and up till now it's always been functions of t on the other side. So we could just integrate and away we went. But if there's sort of this self-reference where the function defines its own second derivative, which defines the function, when we get this circular kind of case, we have to take a different approach. And that's what we're going to learn how to do going forward in this unit. Just for your own reference, the correct solution to this differential equation is actually b. If you try to substitute in x equals cos of 6t into the left-hand side of this thing here, we've done enough derivatives of cosines earlier in this course to recognize the derivative is negative sine times 6. We take another derivative, we're going to get back to negative cos, and we're going to have taken 2 6's out, so it'll be times 36, while the right-hand side is equal to negative 36x, but we said x of t was cos of 6t, so cos of 6t here, and those are exactly equal. And so we verified that this function, when we sub it into the differential equation, satisfies it. And that can make a little more sense if you're like, whoa, what just happened? Read this out loud. I'm looking for a function which does something. It satisfies some property. And the function, when I differentiate it twice, equals itself. Well, what kinds of functions equal themselves when you differentiate them? Well, exponentials, sines, and cosines. Specifically, when we differentiate it twice and we end up with a negative version of itself, well, we know if we differentiate cos twice, we go cos, negative sine, negative cos. Oh, that works. And then the 36, we only get that 36 multiplier if we carefully select our multiplier inside here as the square root of 36, 6 there. Anyhow, we're going to get into how to find this function just given the equation as we work through this unit. But for now, it's enough to recognize that the equations that we're going to be solving over the next little while are of a new kind. And you should treat them with caution as you walk into them, and just be careful to check your work as you go. That'll be the most effective strategy I think you can bring to bear.